So that's pretty unobtrusive.
It is. Okay, so this is an introductory course, but we have to do some amount of these tensor things, and so we have been doing, and I appreciate your patience in keeping up with it, but do keep up with it. It is a lot of work till you get used to it, but it is important that you keep up with it. Good news is the abstract tensor calculus that we're doing ends very soon, and we'll actually write down the Einstein equation. So it's maybe 2-3 lectures away. So recall, and I write this largely for my benefit as well, this is the definition of the Riemann curvature tensor. It's a rank 4 tensor, or some might even say 1-3 or 3-1, I can't remember, but it takes 3 vector fields and 1 dual vector and returns a scalar. And this is a true tensor. And when you take all these covariant derivatives of dual vectors, we still get dual vectors back. But when the tensor, when you contract it with all its indices with some object, you should get a scalar. And so on the right-hand side, they have a dual form acting on a vector field. So you get a scalar function back. This is typically written as R, A, B, C, D, X, A, Y, B, Z, C, and W, D. And it's been fully contracted out. We talked about one result yesterday, and that is actually property 2. We're going to have a list of symmetry properties of the Riemann tensor. We'll have 4 of them. You've actually seen 2, but I didn't mention one of them. The one we saw yesterday was the fact that this is equal to 0, and this is only true, I believe, for a torsion-free connection. We may have used, I think we did. Yeah, it is a torsion-free connection that this is 0. And I called it 2 here because in my notes this is property property 2. I use the word connection. That's traditional. It is literally, I mean, the covariant derivative, which in turn is described by Christoffel symbols, and torsion-free then implies that mu lambda is equal to mu lambda nu. It is symmetric in the lower 2 indices. So going slightly out of sequence, if you will, property 1, this is much easier. So clearly, I mean, this is a statement I'll almost make without any proofs, but if not, you let me know. Is this true, guys? When I say clearly, you should say, yeah, of course it is true. Is this true, guys?
Yes.
Yes, of course it is true. No, why is that? Listen, if I swap x and y, it's like when I swap x and y here, I get this term. But here it's a minus, here it's a plus. Then when I swap this, I get that. When I swap this, I get a negative. So, but in terms of these components, you can see R A B C D is equal to, oh, sorry, not equal to, minus. So yeah, of course it's not true. It's only true with a minus sign. Minus R B A C D. That's property number one. So the components of the Riemann tensor satisfies very useful four set of properties. Okay, so let me do property 3 and 4. They're not difficult. But the next one has a little bit of calculus in it, rather minimal. But the other one is, the last one is just algebraic. So property 3. And this is for a Levi-Civita connection. So that is more than, what do I mean by Levi-Civita connection? Two things must happen. I defined the Levi-Civita connection a couple of lectures ago. It has two parts to it. One is that torsion is 0. The other is that the covariant derivative with respect to any vector field of the metric is 0. Yeah? These two in particular imply that gamma, mu, nu, lambda takes the usual form. I'm not going to write it out. Remember the three terms we have here? So Levi-Civita connection means precisely the old covariant derivative that we've been always using. This one only requires torsion free. This one requires the Levi-Civita connection. Well, what is the requirement? What is the proof? The proof, I mean, what am I trying to show? Is that A, B, C, D is equal to R. And let me make this very clear. Oh, let me color code it. Although it doesn't show well on the video. I don't know why. A, B, C, D is equal to C. I have swapped the two pairs. Yeah. Now, now look at this. This one has 3 indices up and 3 indices down and 1 index up. So when I write like this, what do I mean? Yeah? That's, you lower E and make it, replace it with D, like we've been doing all along. Surely you won't be able to reduce, lower the Riemann indices like you need to, unless you have a GED. So proof. Questions? You guys are awfully silent.
We're just kind of on edge because of the exam today.
I'm sorry?
I think we're just kind of on edge because of the exam.
Oh, exam is over or?
It's going to happen at 1.
Ah, okay.
1? No, 2. Yeah, 2.
Well,
That was like a quiz in scientific computing as well, so it's going to be a bit of a day today.
Let me, in that case, provide you the proof. A, and then I picked G, C, D. On the one hand, this must be 0 because the covariant derivative of G is 0. It's a Levi-Civita connection. On the other hand, this is precisely how you compute the Riemann tensor. So it is R, A, B, C, E, G, let me make sure, R, minus of course, minus R, A, B, C, E, G, E, D, minus R. Now I have to take the derivative of this index, R, A, B, D, E, G, C, E. So I bring one to the other side and I get R, A, B, C, D equals minus R, A, B, D, C. Oh, I did bring this. Oh, that didn't quite work out, did it? CD. That is not what I intended to prove. This is what I intended to prove. Draw with A, B, B, C. That's property 3, sorry. See? R, A, B, C, D has become R, D, C, the minus sign. Because the next, what I wanted to show requires this as well. So note, what I wrote was not what I was showing, but this is what I wanted to show. So that's property 3. So let me make it very clear, just a quick recap. The first one is R, A, B, C, D equals minus R, B, A, C, D. I can swap the first two pairs and I get a minus sign. The second one is R, A, B, C, D. I can swap the last two pairs. Oh, that's the third one in the sequence. I might change the sequence, but I may not. And the second one that I proved was R, A, B, C, D, 0. Let's stop and let me take questions. So what I wrote originally, the swapping of the pairs, I'll do that momentarily. And the last one is what I originally wrote, A, B, C, D, is R, C, D, A, B. So understand the symmetries, and then this one I need to prove. Yeah, I need to prove. So look, what I'm saying is, if you swap the first pair of indices, you get a negative sign. Here, what I'm saying is, if you swap the second pair of indices, you get a negative sign. And here, there's this weird anti-symmetry relationship. Okay? This one is interesting. You can swap it by an entire pair. You can swap AB and CD together. I take CD and move it over here, and AB and move it over there. You don't get a negative sign. It's exactly equal to it. it seems like, well, why are we doing this? Well, for two reasons. We want to understand the Riemann curvature tensor because it plays a very important role in physics, particularly in general relativity. And so when we do calculations, we want to know what's going on. Do you recall where this comes from? We had this, I had shown this before, right? Minus BA RA BC D minus. We had shown this result before. So here there's one index, there's only one term. Here we have two indices, so I do it one for each index. See, first I did it for this pair, like we do it for this pair. I mean, here there's only one pair. So we took the derivative combinations for this index, if you will, and then I do it for, just like when you take covariant derivatives of multiple things. Okay? Again, I need to do this. Property 4 for a Levi-Civita connection. R A B C D equals R C D A B. This is an algebraic, doesn't require any calculus. It's putting all the previous properties together. So, what I'm going to do is I'm going to begin with, we know this. So that means R, A, B, C, D minus R, A, C, B, D plus R, B, C, A, D minus R, B, A, C, D plus R, C, A, B, D minus R, C, B, A, D equals 0. It's 1/6 of that. That is 0. But do you understand how I did the anti-symmetrization? So all the positive terms are cyclic. I have R, A, B, C. Then the next one is BCA. Let's see. BCA. And then the next one is CAB. CAB. And all the negative terms are these two indices swapped. BC becomes CB, CA becomes AC, and AB becomes BA. Okay? All right, that's equal to 0. So then I have, let's see, this is R, A, B, C, D, and what do we have? B, C, D, that's not helpful, C, A. So what I have here is R, C, A, B, D plus R, C, B, A, D. We see A, C, B, D. Oops. A, B, C, D, A, C, B, D, C, B, A, D. Okay. So how did that come about? This term is this term. What about this one? Is this one brought to the other side. Right? So this one is accounted for. What about this one? Brought to the other side. What happens to the other ones?
They just cancel.
Nope, nope, nope. So, for example, let's look at this guy, BC AD. This is the same as what?
ADBC.
No, this is equal to minus R CBAD because of one of the properties. So when you bring it to the other side, I get twice as much as that. Yeah? So then let's look at, there's ACBD, we talked, oh yeah. ACBD, this is CABD. So when you bring it to, so it's an AC, you bring it, make it negative, you bring it to the other side, so this becomes 2. What do you think happens here? This becomes 2. So, and divide by 2 to get this relationship. So there are many relationships that we use. So what I'll do, I'm going to use the same labels. This is chapter 7, equation 13, so I'm going to call it chapter 7, equation 13. Like I said, it's algebraic. I'm going to write 2 more equations like this, and we won't even pay attention to it. C from R, C D A B equal to 0. Just like that, you will get R C D A B is equal to R C A B D plus R C D A B. I want to make sure. C D A B, okay, and C A D B, C A D B, and A D C B. Ah, gosh, maybe this A D C. One more time. C D A B, yeah. C A D B, good. A D. What? Why do I see it differently every single time? What's the condition for that? Is that just dyslexia? C D A B. Tell me if that is right. Okay, C A D B.
CADB.
A D C B.
Yep.
Yep, and this is 714. That isn't enough. We'll write 2 more. And it's in your notes, but let me write the result. R C B D A. Or C D B A. By taking different combinations, and I've written the details in my note. I want to do the part in the notes that is not in the notes, or DBCA. And this is 715. See? Or CBDA, good. CDBA, DBCA. One more, that is R DABC, R BADC. D A B C, B A D C, D B A C. So we have 4 equations. Like I said, this is just algebraic. They all come about by writing out stuff like this. It was this combination, and there are 2 other combinations that is given in your notes. So let me, I'm going to erase that part, so I'm going to write R, A, B, C, D equals R, A, C, B, D. Or C, B, A, D. And call that 7. Okay, so it is really, and what we want, I'm going to erase that word, is R, A, B, C, D equals R, C, D, A, D. This is what we need to prove. So let me put one equation into the other. And I've just stated them in the notes, so let me be careful here. So what I'm going to do is put 715 into 713. And what I get is R, A, B, C, D equals R, substituting 715 in equation 713, R, A, C, B, D minus R, C, R, C, I'll show this, C, D, so many indices, R, D, C, A. So I'm taking this and putting it over here. So I have R, A, B, C, D. And I have A, C, B, D. So I have this is this. So then I have C, B, A, D. Correct? C, B, A, D. But what I have here is C, B, D, A. But what is C, B, A, D? It's a negative of this. So these 2 negative terms. And I haven't changed the orderings, D, B, C, A. You see that? So this is AD, so this is DA. But DA is a negative of this, so you put 2 negative signs. And so the last one, of course, we pick the other, I take this and put it in here, and I don't need to go through the algebra. And then I have R, C, D, A, B equals R, C, A, B, D plus R, B, A, D, B, A, D, C plus R, D, B, A, C. So if I take this and put it over there. Now I'm going to subtract the 2. So this is, say, 1. This is 2. So 1 minus 2 is R, A, B, C, C, D minus R, C, D, A, B. Obviously, these 2 are equal. Whatever is happening on the right-hand side, I should get that to be 0. So I would get R, A, C, B, D minus R, C, D. And you have to tell me what terms cancel. D, please make sure I'm copying it correctly, minus R, C, A, D, B minus R, B, A, D, C minus want. Hopefully I've not made an index mistake, and that's why it's very important to do this. Minus CDBA. The last one is BADC. BADC. That doesn't help you. Okay, let's try. There might be a mistake. This should add up to be 0. Will these two cancel? Yes, they will. Because when you swap here, you get a negative sign. But when you swap here, you get a negative sign. Negative, negative is positive. But this is positive, this is negative. So I feel like one of my index is wrong, and we'll catch it, and I'll fix it in the notes. Look at this one. Yeah, this is CA, this is AC. So this becomes a plus, and these two cancel. Obviously, this should cancel unless it goes to the other side. Yeah, so it is correct. All right, so let me, if we lose this, we just lost everything. So I have R, A, B, C, D minus R, C, D, C, D, A, B is equal to minus R, C, D, B, A, minus R, B, A, D, C. So first of all, watch what I'm going to do. It's correct. I'm going to swap these two and these two. So when I swap here, it becomes just A, B, C, D. In each pair, I get a negative and negative. Negative and negative becomes a positive. This is the same as that, so I bring it to the other side. So I erase this and make it a 2. Now, what about this? Same thing over here, right? This becomes an AB with a plus sign. So when I bring it to the other side, I would get this equal to 0. And hence, R, A, B, C, D, C, D, A. So let me recap property 1. You can, at this point, take this for granted. Whenever you need to, you just come back and look at it. Minus R, B, A, C. Property 2 is the weird one. I can put this up or down, it doesn't matter. Property 3 is R, A, B, C, D equals minus R, A, B, D, C. Here I swap the first pair, here I swap the second pair. Fourth property is swapping it pair by pair. You see the pattern? These are the 4 properties of the Riemann tensor. So what you should do is at this point, you should write recap the 4 properties. Make sure you know the derivation, but I don't think my exam has to do necessarily with the derivation. It's in the notes. You don't commit it to memory, but you understand where it's coming from. Before I define the Einstein, define the Einstein tensor, I need one more result. It has a general context, but I think I don't have enough time to prove it. This is called the Bianchi identity. looks like this, but it doesn't. This one, like I said, there are two more calculus things that we need. Two more calculus things that we need. This is, of course, when torsion is 0. I have, check this out, R, B, C, D, E equal to 0. What does this symbol mean? These three indices are anti-symmetrized. It's almost like this, but we're shifting and just taking the first two, and then putting a covariant derivative. This is not complicated. It seems complicated, but it's not. So I have A, B minus B, the usual of what we do, except normally we would take a W over here. But that's okay. We'll do C and W D. We did something very similar. We did this for like G, GCD. Except instead of GCD, we have, it doesn't make a difference at all. So let me write it out first. So first I take the covariant, the Riemann, this is a Riemann combination with respect to this index. So I put the A, B first, and then it's a C index, and then I have to put, I can't use it, D, so I pick an E, I think, yeah. E, W, D, minus. And let me, oh, this is also minus. Let me see if the camera gets slightly beyond that screen. Maybe not. And minus R. I notice I don't have a minus sign in my notes. A, B, D, E, C, W. I have to correct my notes. Again, I'm using the fact, till it's just instilled in our minds. I want to continue to refresh. This is the formula that you need to recall. The A. You see, you have A, B, and C. So A, B, and C. And this is the one you're taking derivative, this index, so to speak. See? Right? Weird. Because there are C and D here, well, maybe I should put these are the two terms that I take derivatives of. Now, just to make life interesting, I'm going to pick another one. I'm going to do this. CB of W, what was it? D. But what do I do with that? Well, first what I do, for negative sign, because this is going to give me a negative sign. And then I'm going to get this, and I have R, B, C, D, E, W, E. But then I have to take a covariant derivative of this guy, which is not so difficult to do, which is equal to minus WE. First I take the covariant derivative of the Riemann tensor, R, B, C, D, E, minus R, B, C, D, E, A, W, E. And just use the product. So I have two equations. This is equation 1, and this from here to here is equation 2. In the claim, I'm going to use one fact, which is I would like for you to verify this. If I do B, C minus, I'm going to bring this in, A, C, B, W, so I have anti-symmetrized A, B, and C, left B alone. And if I anti-symmetrize the same thing over here, which is what? A, B, C, then I have W, D, minus B, A, C. So I take equation 1 and I anti-symmetrize indices A, B, and C. I get this. If I take equation 2 and I anti-symmetrize A, B, and C, if you expand this out and expand this out, it will come out to be the same. Correct? That's the claim. I'd like for you to verify. There's no calculus here. You're just writing A, B, C in 6 different combinations for this one, and 6 different combinations for this one, 6 different combinations here, 6 different combinations. So although this looks different from that, the anti-symmetrized product of the left-hand sides are equal. If the anti-symmetrized product of the left-hand sides are equal, what must be true? The anti-symmetrized product of the right-hand sides must be equal, right? Because the two equations have left-hand sides and right-hand sides. If the anti-symmetrized versions of the left-hand sides are equal, then the anti-symmetrized. So what I'm going to do is anti-symmetrize this for A, B, and C, and this for A, B, and C, and then set it equal to each other. I totally don't have the space, so you have to bear with me. When I do that, I would get R, A, B, C, E, W, E. No, plus. I have to explain this notation. A, B, D, E, C, equal to WE, and I'll first verify the accuracy, and then I'm R, B, C, D, E. I'll have to explain this notation. D, E, accuracy. R, A, B, C, E, okay. A, B, D, E, C, W, B is equal to W. R, A, B, C, D, E plus R, B, C, D. Okay. That's all we need. I need to explain this notation. What is confusing about this notation? What is new about in this equation? What's the new notation you've seen?
It looks like absolute value.
Yeah, it looks like absolute value. This means we anti-symmetrize everything from here to here except this one. Because we're only anti-symmetrizing A, B, and C. Correct? So whenever you see B, C, D, A, don't anti-symmetrize. Just leave it there. Well, if you want to be explicit, I can give you the first term will be B, C, D, A. We always leave D where it is, okay? And then minus B, A, D, C, right? Left D where it is, and I swapped. The next one would be, I start with C. C, A, B is over here, and then B, C, A, D stays there, and B, minus, this is A, C, B, D, A, correct? And then the last term will be A plus A, B, D, C minus A, C, D. Hopefully I've not made a mistake. So D is always in the third position. B, C, A, B, A, C. C, A, B, C, B, A. Good. A, B, C, A, C, B. That's what I Okay? But from property number 2, this is equal to 0. These two terms are identically the same. Why is that? Because it's a cyclic permutation. If you expand it out, look, I have A, B, C. The next positive term is B, C, A. That is B, C, A. So this is equal to 0, and this is equal to that. That can happen only if this is 0 for every W. How can it be 0 for every w? You can make the first component 0, second component 0, third component 0, fourth component 0. This can happen for every w only if n. And this is in fact the Bianchi identity. So it's a lot of tensor calculus. I don't want you to memorize the calculations, but two things. You should know the results, so you have the 4 symmetries of the Riemann tensor and 1 Bianchi identity. You should write that down as a recap. The other thing you should know is if you look at the proof, you should be able to follow every step. Fair? We have one more tensor calculus calculation, and then we have the Einstein equation. And then it's back to talking about specific solutions. No abstract tensors all the way. Although that stuff is good, and that stuff is very important,